Okay, so we're going to continue where we left off on Tuesday with continuing with proving big O characteristics. Basically, given two functions, you want to show that f of n is big O of g, right? If you're able to show this inequality, basically, you're showing that f of n is big O of g of n, right? And I showed you the one approach last time. That approach meant that you fixed c to be 1 so that it went away, and then you tried to find the crossover point, basically. And with the example that I gave you, that was easy because it was only a degree 3 polynomial, so you could immediately take out one of those roots, and then you could apply the quadratic equation to get the other two roots, and then you could reason that way. But if I gave you a degree 50 polynomial, are you going to go out and try to find all 50 roots? No way. So instead, I'm going to show you approach B. And there's also an approach C, but for that, you'll have to watch the videos because it requires calc, setting up a limit of the ratio of two functions and then finding if it diverges or converges to something, blah, blah, blah. I'm going to show you approach B, which is just the opposite. Again, we've got two unknowns here, that coefficient out front, and then not, in other words, those functions will cross over at some point and then never meet again, meaning that this function will always be on top after n naught. So what we're going to do is we're going to fix n naught to be, say, 0. We'll start at 0. Maybe we might have to go up to 1, might have to go up to 2. It doesn't really matter. But then we're going to find c, right? And by doing that, basically, you just need to set up f of n, and you need to show that it's bigger, less than or equal to, say, 2f of n, right? And here at this point, I'm going to be less abstract about it. What can you say about, say, just x? Right? If you want to make it bigger, you can definitely say that x is less than or equal to x plus 1. Right? You can definitely say that x is less than or equal to x plus 10. In other words, you can add stuff and make it bigger. You can multiply and make it bigger. Right? I could say that this is less than or equal to 2x plus 10. Now, in general, is this true? What if x is negative 1,000? Does this inequality hold? No. But do we have negatively sized inputs? No. So we're only looking at x's for all x greater than or equal to 0. Right? That certainly holds for all x greater than or equal to 0. So that's the basic approach that we're going to take. That I need to start with f of n and then make it bigger and bigger and bigger until it looks like c g of n. Right? And by doing that, I've basically fixed my n naught to be 0. And then I'm finding this coefficient out front. Right? I'm making f look like g with some constant coefficient out front. Fixing n naught, finding that c gives me my proof. Okay? Now, one way, before I actually show this, I'm going to describe what this means graphically. Right? So our examples from the last time, let me check what they were. I forget now. It was like n cubed. Right? So I don't have different colors. I thought I had different colors. Oh well, I want a pencil anyway, because I want to pencil with the tip. There we go. So n cubed is going to be initially lower, and this is not at all accurate here, than, what was it, 100n squared plus 50n, something like that. Right? If you graph that, it looks something like this, where before 100, right, n cubed is below. In other words, it's the better function because it takes fewer resources. And this one was 100n squared plus 50n or something, right? And then at some point, say at this crossover point here, 100, then this one, then n cubed becomes larger, and so this one becomes the better function because now it's always below, meaning it's taking fewer resources. Now, what would happen if I multiplied n cubed by 2, right? So if I went, say, 2n cubed, it would look something like this, right? 2n cubed. What have I done to the crossover point? I've moved the crossover point from here down to here, right? Now, still, I don't know what this crossover point here is, but still, this n cubed function is still below. Oops, sorry, I should have. Yeah, it's still from here to here. It's still below this one, right? But and the video does a much better job of this because I'm drawing it physically here rather than I prepared those slides in the videos. But it still gives the misimpression that at least from here to here, that this algorithm is better than this algorithm? Well, there's nothing special about 2. What can you do to it to make it even larger? Right? You can make it 3n cubed. Now look at all these 3. Am I changing the rate of growth on any one of these? This is a cubic, this is a cubic, this is a cubic. All I'm changing is the constant coefficient out front here, which ultimately we don't care about because we're doing big O analysis here. And so for a sufficiently large enough c, n cubed, then we get this crossover point moving all the way back from here to here to here, all the way back to 0, which is exactly what we want. Because I'm fixing n naught to be 0, and I'm just bumping up this function until it lies completely above this other function over here. Right? All right. So let's actually do it for these 2 functions right here. Right? So we want to show that 100n squared plus 50n is less than or equal to c n cubed for all n greater than or equal to n naught. Now, again, what I'm going to do is I'm going to set this to 0. Right? And now I need to find the c. So to do this, I'm just going to show a series of inequalities here. 100n squared plus 5n, or sorry, I think it was 50n. We'll go ahead and go with 50n here. Right? Is less than or equal to what? How can I make this thing bigger so that it eventually looks like this thing over here? Let's focus on this lower order term here first. How can I get it so that I collapse it into one term? What is 50n less than or equal to for all n greater than or equal to 0? How can I make this? I can make it 100n. Right? I can make it 200n. Right? What could I do to the n, though, so that it would collapse with this one over here? Square it, right? Multiply by n. Instead of multiplying by 2 by a constant, multiply by n. 50 times 2, well, that bumps it up to 100n. But 50 times n, that bumps it up to 50n squared. So n squared plus 50n squared, right? For all n greater than or equal to 0. Right? That's certainly true. And now this thing, carrying this down here, is equal to 150n squared. It looks almost like this, right? I've got a constant out front, c, 150, but it's n squared. How can I make it look like that? Just make another inequality. How can I make this bigger? Do it again. Multiply by n. 150n cubed, right? And then for all n greater than or equal to 100, for all n greater than or equal to 0, right? So for n naught being 0 and c being 150, f of n is less than or equal to c g sub n for all n greater than or equal to n naught. Right? Therefore, f of n is, big O of g of n. And that's what we wanted to show. This thing has a higher rate of growth, right? And it's a simple enough proof. All you have to do is make it bigger, 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 bigger. Don't make it too big. If I went all the way up to, say, n to the 4th, that's going way too far, right? Now it's even bigger than this thing, right? And that's not what I'm trying to prove, okay? All right, you'll get plenty more practice as you look at more and more functions. But otherwise, you just make it bigger, right? Linears are larger than logarithms for all n greater than or equal to 0. Are logarithms defined for 0? Nope. So linear functions are greater than or equal to logarithmic functions for all n greater than or equal to 1. In those cases, you do have to bump it up. Exponential functions are bigger than polynomial functions, etc. Right? In fact, we can come up with a whole hierarchy of functions here. Give me one function. What's the lowest order function you can think of? Okay, some constant term. I could put 5 in here. I could put 10. I couldn't put 0 because it doesn't cost you anything ever, right? So instead, I'll simplify it to 1, right? This is constant. Give me something large. What's a very fast-growing function? Oh, okay. So order n factorial. This is called super exponential. because it's even larger than an exponential. You can apply Stirling's formula and you get the n to the n, which is bigger than any exponential function that you could find. For example, order 2 to the n, right? Or order 3 to the n, or et cetera, as whatever base you want to put here, as long as it's greater than 1. But not all exponentials are created equal. This is definitely a faster growing function than this one over here, right? But they're both exponential. Right? What else? We're going to look at it in a moment here. Binary search. If I gave you an array of an sorted array of size n, about how many comparisons would it make? Log n. So we've got logarithm functions, right? And I'm not writing the base here because we're computer scientists, self-respecting computer scientists use base 2 all the time, right? So logarithm, or logarithmic, right? And I'm leaving a gap here. What else is there? Linear, okay. Order n would be linear. What if I combine these two? What if I had an n and then a log n, like, say, sorting algorithms? Order n log n. This is usually referred to as quasi linear or quasi polynomial in general. It's quasi because, you know, almost linear, right? This lower order term logarithm here, yeah, it's going to grow along with n, but it's going to grow so slowly that, for all intents and purposes, it's almost linear, right? So quasi linear. Right? Then, of course, you can go up to n squared, n cubed, dot, 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 and now I've run out of room, so order n to the k. All of these things are just polynomials. Right? Now, in the real world, where we've got moderately large data, we've already seen, is n squared acceptable? Probably not. Not for moderately large data, right? I am going to just say that these are all feasible algorithms. Even if order n squared, you know, theoreticians love polynomials because they're all less than exponential. But even a polynomial like n squared in practice is not acceptable, as we already seen. If I've got an order n squared sorting algorithm and I want to sort a billion elements, nope, it's taking several hours at least to do that. If I'm using a naive linked list to sum things up and it ends up with n squared and I've got a billion elements, or maybe it was 10 billion, I forget which one it was, the time that we extrapolated out of that was 20 years. That's not feasible. Right? Anything below, however, is usually feasible. Now there's, you have big data, then maybe even linear is not feasible depending on how large your data is. Okay? This is, of course, is the gold standard. If you can do everything in a constant time, then you go for that, right? But these are theoretically feasible, theoretically good, and these, of course, are never good. Never good, except for very small inputs. Right? And by very small inputs, it depends on how fast your computer is. What about 2 to the 100? Or let's say 2 to the 1,000. 1,000 small, right? But with respect to an exponential, 2 to the 1,000, how big is that? It's bigger than the universe, right? I forget what the exponential is, but 2 to the x, maybe it's 100, maybe it's 200 or something. That's more than the number of atoms in the known universe or something, right? So even 2 to the 100 is not feasible at all. 2 to the 8, sure. 2 to the 8, that's only, what, 1,024? 2 to the 10, yeah, okay, that's getting up there. No, 2 to the 8, sorry, is 256. 2 to the 10 is 1,024. But you start getting up to 20, 30, right? Those start to become infeasible. And even, those are feasible for very large computers, right? That's how you do hash breaking a hash function or something like that. But once you get up to 2 to the 40, 2 to the 50, there's not a computer in the world that's going to be able to handle that. but 2 to the 1,000 is out of the question. Okay? So those are the classes of functions that you might see. With the remainder of today, I wanted to revisit some other algorithms that you've seen before. The first one, and one maybe some that you haven't seen before. One of them that I wanted to get more practice doing all this stuff with is insertion sort. Just because probably among the bad order n squared sorting algorithms, right? By the way, we've seen examples of each one of these things before, and we'll see a couple again. Like, for example, just computing a formula, Gauss's formula or something like that. That's going to be order 1. Binary search, which we'll revisit here in a moment, is order log n. Any linear function, like summing up things in an array, right? That's going to be linear. Order n, quasi linear, merge sort, quick sort, Tim sort, all those kind of things. The good sorting algorithms are going to be order n squared, or order n log n, excuse me. Order n squared, that's where we get into those every pair, right? Or naively, the painter's problem, where he starts at the one side of the fence and then goes, doesn't pick up the paint bucket with him, and so has to go back and forth, right? Things that lead themselves to the behavior of Gauss's formula, which is order n squared. And then, you might have seen something like this, 2 to the n. That's all possible subsets, maybe, if you've been looking at that in 235. Order n factorial. Who said that before? Where have you seen order n factorial before, maybe? Not subsets, but something else, some other combinatorial concept. So if I've got 6 people, or if I've got 5 people in a row, how many ways are there of arranging them for a picture? Permutations, 5 factorial, right? There are 120 ways of doing that with just 5 people. 6 people, 720. 7 people, I don't have that, 7 times 120, whatever that is, right? All right, or 7, whatever I said, right? So we've seen examples of all of these, but now let's see revisit some of those examples. Insertion sort, you might not have seen it before, so let me go ahead and tell you how it works. I'm going to jump into the middle of the algorithm. The algorithm starts by considering, at one end, and starts inserting things where they belong. So let's just go ahead and assume that we've got 10, 20, 30, 40, right? And then, I don't know, 25, 82, 7, and 3, right? If I jump into the middle of the algorithm, then this is the sorted section, right? This is what's been sorted so far. The algorithm works by looking at the next element and then going back through the sorted array, finding out where it belongs. It makes a comparison to 40 and says, well, it belongs before 40. So what does it do? It swaps these two things. And then it looks at 25 and 35 and it sees, well, 25 is less, so it swaps those two things. And then it looks at 25, which is now here, and 20 and says, oh, well, I don't need to swap that anymore. So this would have ended up swapping, this would have ended up swapping, and then 25 would have ended up right here, right? With 30 and 40 right here. So out at the end of this iteration, I would have 10, 20, 25, 30, and 40. Still 82, 7, and 3. And now this is sorted. Right? If I did that again, 82, I compare it to 40. Do I need to swap those? Nope. So I don't end up swapping, and that's the end of it. Right? Now this is sorted. Now 7. I need to insert it where it needs to be. So I make a comparison. That's less. Comparison. I make a comparison, 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 and I end up make a comparison here, and then I end up inserting it all the way down here. Right? So I made 1, 2, 3, 4, 5, 6 comparisons. In the worst case, and then on the next one, it'll be even worse. I'll make 7 comparisons. But the point is that sometimes you only have to make 1 comparison to insert it. Other times, you have to make a bunch of comparisons to insert it. In other words, it's kind of adaptive. Unlike selection sort, when we looked at that, you had to make all those comparisons no matter what, because you didn't know where the minimum element was. So you compared this to everything else in order to ensure that that was the minimum, so that you inserted it, you selected it, and then put it at the front of the list. This is more adaptive. If I've got a large section of things, or things are already sorted, like 82 is all the way down here, then I don't need to do a lot of comparisons. I don't need to do a lot of swaps to move it down. Okay? Where do you start out? Well, if I started out, and this is all a big jumble here, if I started out over here with an array of size 1, guess what? By definition, it's sorted. So where do I start? I start by assuming that the first one is sorted, and then I start at the second one, and I start comparing that to everything before it. Right? That's the basic idea. So let's go ahead and get some more practice writing some pseudocode. So here's insertion sort. And hopefully I remember this off the top of my head because my battery is about to die. Otherwise, I don't know if I've got it up here. OK, yeah, good. Just to remind myself of this. So the input and the output are the same as, say, selection sort. The input is going to be a collection of elements, and I'll call them A1 through AN. Now in the example over here, it was easy to use integers, but over here I'm making it more abstract. I don't know what they are. I don't care what they are. It could be integers. It could be strings. It could be student objects or invoice objects. Right? A, sorted, is what we're going to output. Okay? So again, I assume that the first one is sorted, so I need to start at the second one. Right? So I will start an index variable here at 2, remembering that I am using one indexing. So if you were to translate this to Java, of course, you would start at I at 1, the second element being at that index. Okay? And then I'm going to go up to something. We'll go ahead and come back and determine what that should be later. Right? What I'm going to do is I'm going to start at element a sub I, right? Compare and swap it down the array until, when do I stop? When did I stop over here? On the first iteration, 25, that I swapped it if a sub I, this element right here, was less than a sub I minus 1. Right? If this is less than this, then I swap it and I decrement my index variable. So to keep track of that, what I'm actually going to do is I'm going to, instead of always comparing it to index variables, what I'm going to do is I'm going to store off the variable a sub I. Yeah, there we go. I'm going to call it x, so that I'm always, here's my x over here is 25, right? So I'm always comparing this current variable to this variable up here. This variable doesn't change. So it's just a convenience thing to simplify my pseudocode here. I'm going to compare x to I minus 1, I minus 2, I minus 3, until this the current one that I'm looking at is, let's see, I stopped here, is less than x. Right? So while the current one that I'm looking at, so in other words, I need a current one, what I'm going to do is I'm going to set up another index variable here, j. Because if I set up if I use I here and decrement I, that kind of screws up my outer for loop here. So I'm going to set this up to j. While some condition, I will swap a sub j and a sub, I don't need to swap, right? I just need to shift stuff over, basically, right? Insertion sort, I need to shift this over. I don't need to swap them every single time. Since I've saved this off into a variable, I'll shift this up, and then I can insert this at the end. Right? So to shift it up, how do I do that? A sub j is going to be equal to the one previous to it. How do I get the one previous to it? A sub j minus 1. Right? Good. And then in a slightly bad fashion here, I'll go ahead and decrement j, minus minus. Right? If you wanted to do proper pseudocode, it would be j, left arrow, j minus 1. Right? Basically, all I'm doing is I'm shifting these things up. On this iteration here, I shifted 40 up so that I made room for it. Then I shifted 30 up so that I made room for 25 eventually. And then I put 25 in there. Okay? So at the end of this while loop, I need to make it so that, here we go, a sub j takes on that x value, that temporary value. And that's the end of my for loop. Now, now I need to go back and fill in some of these conditions here. When do I continue going on? Remember, I'm currently looking at a sub j. A sub j versus x. I need to make the comparisons between these two. A sub j and x. Should I be looking at less than or greater than? We just need to get this right. So I'm looking at the current variable here, and I need to swap it if it is greater than x, right? So if the current variable that I'm looking at is greater than x, shift it over to make room for it, right? And then go down to the next one, right? And where do I stop? What's the last, if I continue this, if 7 was inserted over here, do I have to look at this last one? Is it in order? Where does it need to be? All the way back to the beginning, right? So I definitely need to look at that last one, right? And there's insertion sort, okay? Now, the analysis of this is going to take more than I want to do in class. If you want to, I think I do it in the video. I'm not sure. But here's the basic idea. So suppose that we're at a sub I, right? And elements a1 through a sub I minus 1 are all sorted. This is the current one. I should have just drawn my arrow up that way. All right? And then the rest of them are unsorted, ai plus 1 dot 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 a sub n. Right? So to insert a sub I at the correct location, let's just look at one iteration of this. Requires how many comparisons? Right? Well, remember, sometimes we got lucky. Right? In the best case scenario, how many comparisons would we have to make? 1. Right? So best case, 1. Right? What about the worst case scenario? Like, say, with 7, where we had to move it all the way back down. I would have to compare a sub I to this one, and a sub I minus 1, a sub I minus 2, a sub I minus 3, dot, 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 all the way to a sub 1. So in this iteration, how many things are right here in this sorted list right here? There's 1, 2, 3, 4, all the way up to I minus 1. So worst case is I minus 1. Now remember when we looked at linear search and we said, well, this is the best case, we can't always assume that. Here's the worst case, that's probably what we'll go with. But then we also looked at the average case complexity, right? Because that gives you kind of a real world situation, a real world that in practice, this is going to make roughly this many, right? And we came up with roughly n divided by 2 on average. So if I do the same approach here, the same naive analysis here, what would be the average case? If I take, what did we do with the linear search? I just took the best case and the worst case and I averaged them together, right? So if I take this and average them together, what do I get? Roughly. I minus 1 plus 1 divided by 2 is going to be what? I divided by 2, right? Okay. Let's go ahead and actually focus on that one, I divided by 2. Now, this was just one iteration. You do this iteration how many times? You do it for I being 2, 3, 4, 5, 6, all the way up to n. So in total, if I were to do this, then I would be running from 2 up to n of, and we'll take the average case complexity here, I over 2. All right? Now, hopefully you know that if you've got a constant sitting up front here, which is 1/2, you can actually pull that out. It doesn't matter with the summation, because every term in the summation has that coefficient. And you're left with a summation of 2 up to n of I. Do we remember what this is by now? What is it, at least what it's called? We can look it up. What famous mathematician came up with a closed form for this? Gauss, right? This is Gauss's formula. This is going to be 1/2 times whatever Gauss's formula gives us. Note here we're not starting at 1, so it's going to be off by 1. It's going to be, technically, it's n times n plus 1 all over 2 minus 1, right? I don't like that kind of stuff, so forget about it, right? Throw that out, who cares, right? And this is still an overestimate, right? So technically, if you want to be correct, it's still less than or equal to. Right? Why? Because I took off a negative. I added 1. Right? All right, well, now if I expand this out, what do I get? I get 1/4 n squared plus 1/4 n. This looks very much like selection sort. But the most important term here is going to be is n squared. Therefore, insertion sort is order n squared. So if you just looked at asymptotic analysis, then you'd come to the conclusion insertion sort and selection sort, they're the same thing. They're both quadratic algorithms, throw them out. Right? However, by going through this average case and maybe even benchmarking it like you'll do, or you did. Did you do that yesterday? No, you did recursion yesterday. So like you'll do next week in lab, you will be running all of these algorithms and benchmarking them. We give you the framework to do that, to see how fast each one is relative to another. You'll find that insertion sort is, on average, it's twice as fast as, say, selection sort. Why? Because when you ignore the asymptotic analysis and you look at the actual constant coefficients out front, this is 1/4. What was it with selection sort? Do you remember? It was 1/2. So this is 1/2 of 1/2. So it's twice as good as selection sort in practice. Right? So if you are going to go with a quadratic sorting algorithm, it's best to go with insertion sort. Okay? Let's look at another algorithm that we've seen before, hopefully. Binary search. So remind me how it works. The input is actually a special input. It's an array, or a list, or something with random access, so that you can jump to the middle. I'll call it an array of elements. But what condition do we have to have for binary search to work on an array of elements? It has to be sorted. Sorted. Well, we know how to do that now, right? We've got several sorting algorithms already in our pocket. All right, what's the output? And a key. Okay. The output will be an element, A in A, such that A is equal to K, or phi if no such element. Very similar to what we did with linear search, right? I'm not outputting null. I'm not outputting -1. I'm not throwing an exception. I'm just outputting this special mathematical symbol, phi, right? Remind me how it works. Let me go over here. Right? If I've got 10, 20, 30, 40, 50, 60, and 70, and I want to search for, say, 20, how does it work? So you start at endpoints right here, right? Left and right. And what you do is you jump to the middle and call that M. And then you compare your key to M. 20 is less than 40. So if 20 exists, and it does because we can see it, right? Then where does it exist? Does it exist in this half of the list or this half of the list? This half of the list. So throw this half of the list out, and I've got a list half the size, right? And now I basically update my R here. That's my new list. Now my new M is right there. I compare 20 to 20, and I find, oh, that's the thing I'm looking for. I don't go any further. I don't recurse anymore, right? What I'm going to do is I'm going to write the recursive version of this, which you may or may not have seen. I forget how we did it last semester. But I'm going to set up the recursive version of this, right? So in addition to A, an array of elements A, sorted, and a key element K, I'm going to input bounds, left and right. Initially, they're going to start at the endpoints, right? L is going to start over here at 1, R is going to start over here at n. But recursively, when I jump into this, I've got L and R. Right? Now, when do I, the first thing that you need to do with recursive algorithms is you need to know when to stop. All right? So I've got L and I've got R, and I'm moving this over, moving this over, moving this over. When do I stop? When they're equal, I still want to make sure, well, is this the key or not the key? Right? But when do I want to stop? When they go past each other. Once they go past each other, then I know that's an unsuccessful search and I can return. Right? So how do I tell if they've gone past each other? Here's L and here's R. What kind of equation should I set up, an inequality to determine if L is less than, well, L is less than R, because this is a stopping condition, right? All right, sorry, I started with L. If L is greater than R, there we go. Right? So if L is greater than R, then output V, right? Because they've crossed. Right? If L is less than or equal to R, right, like this, or they're equal now, I want to keep going. Else, right? If, what's another condition where I can stop? If L is equal to R, right? They've met in the middle. What should I do? I guess I don't have to technically do this, but I could just make one more comparison. Is that the thing I'm looking for? Is it equal to K? Right? But I'll go ahead and subsume that with the following. Right? So I need to look at the middle point, M. How do I get M? Right? This was index 1. This was index 7. Right? How do I get index 3? Or sorry, 1, 2, 3, 4. There we go. How do I get that? If I've got 1 and 7, it's the average, right? So what's the average? It's going to be L plus R divided by 2. L plus R divided by 2. Right? And I don't know whether or not I went over it last semester, but in practice, you would never do that. Right? That's susceptible to overflow right there. So you'd want to come up with a different way of looking at that. Right? You don't want to start out at, what is it? R minus L divided by 2 plus L. Right? That will not get you overflow. But this is pseudocode. We don't care about that. Right? There is no overflow in pseudocode. All right, so I've got this middle element, and I need to make checks. If a sub m, the thing sitting in the middle, is less than the key element, right? Then that means that the key element, if it exists, where does it exist? So a sub m, 40, is less than, say, 60. That means that it exists over here. So I need to make a recursive call to binary search, passing in everything that I've got up here, the array, the key, but now I need new bounds. They're not going to be L and R anymore, right? What should my new bounds be if I want to recurse on this section of the array? What's the next one over? M plus 1. Does R change? Nope. That's still in my scope there. So it'll be M plus 1 and R. Right? Else, and I'll go ahead and be explicit about it here. Else if a sub m is greater than k, right, then that means that we need to recurse on the left side of the list, so binary search on a, k, and now my L doesn't change, but my R does change. What does it change to? It goes from M down to M minus 1. All right? Else, and then I'll come back up here, else, and what's the last possibility? A sub m is equal to k, in which case what do? We stop. We found what we're looking for. Output a sub m. Right? There we go. That's binary search. It's the recursive version of binary search. I would never actually implement the recursive version of binary search. I would just use a while loop and update things, right? All you need to keep track of are the bounds, L and R. They're moving over, they're moving over, they're moving over. All you need is two temporary variables and a while loop with the negation of this statement to continue. Right? This is a stopping condition. You flip it, it's a continuation condition. Okay? How do we analyze this thing? That's a good question. Well, do you see a loop here? Nope. But you do see recursive calls. Remember last semester, one of the ways I introduced recursion is a replacement for a basic for loop or a while loop, right? That you can carry things forward or you can decrement things using recursion, but why when you've got this nice for loop over there, right? But, and again, why would you do binary search when you've got this nice while loop, right? Good question. When you have it like this, though, and you're stuck with this, how do you end up analyzing this, right? You need to analyze it recursively. So in other words, you need to set up a recurrence. So to analyze recursive algorithms, you set up a recurrence relation. And some of you might be doing this in 235 right now. Second order linear homogeneous recurrence relations, right? Or kth order linear homogeneous recurrence relations. Nonlinear, we're going to come up with a nonlinear homogeneous recurrence relation here, and non-homogeneous as well, sorry. Right? So we're going to set up a recurrence. I'm going to show you how to do that. Basically, I'm going to define a function here. Let C sub n be the number of comparisons by binary search on an array of size n. And so I've chosen C here to stand for comparisons. N is the input to this function is capturing the size of the array. Okay? Now, I just need to get a hold on this, C of n. What does it look like, basically? Right? So if I come into this on the first iteration here, where am I doing comparisons? I'm doing a comparison here, but that's necessary for the control structure of the algorithm. Remember, we ignored those things in for loops. I'm going to ignore that thing in base conditions for a recursion, which is, again, recursion is just a loop anyway. So this is not the thing that I want to be looking for. This is an addition and a division. Actually, it's just a shift because it's the division by 2. But that's also necessary for the control structure of the algorithm. Where am I doing my real comparisons here? 1, 2, 3. Right? Now, first of all, if you were actually writing this code, would you need this third comparison here? No. Right? Because if it's not this, then it has to be this. It would just be an else condition. So I've already eliminated 1. Now we're down to 2. Now, is this really 2 different comparisons? If you feel strongly about it, fine. Go ahead and say that there are 2 comparisons for every call to this function. I'm not that strong. I'm not going to feel that strongly about it because in practice, if I were to actually do a real comparison, what would it be? It would be a call to a comparator function. And that one single call to a comparator function, that's my elementary operation. Not necessarily like comparing 2 integers less than or strictly less than, strictly greater than. You might have an argument that that's 2 comparisons, but this is just a theoretical analysis of this. So I'm just going to say that there's 1 comparison here because I want to simplify things. Right? So there's 1 comparison to see if k is equal to a sub m or which side you recurse on, right? But is that it? So is this a constant time algorithm? Do we stop there? So let's assume this case, that we need to recurse on the right-hand side, or the right side of the list, right? Do we only do 1 comparison and then this takes care of everything for us? We never do another comparison? Nope. We are making a recursive call here. We're making a recursive call And so we need to count the number of comparisons made in that recursive call. Guess what? We have a function that tells us that, c sub n, right? So we make one recursive call here, but is the array the same size as the array of size n? How big is the array here when I look at m plus 1 to all the way up to r? How big is it now? Before, coming in, it was n, right? But now it's what? I've cut it roughly in what? When I did it right here. I cut it, either do this one or do this one. I cut it from 7 down to just 3. I cut it in half, right? So what, and I only make one or the other. These are two mutually exclusive conditions here. I either make a recursive call on this one or a recursive call on this one. It will never be both. So I need to add c sub n divided by 2. This is the number of comparisons in the single recursive call. Right? And now I've captured them all. Let me go ahead and, without text here now, let me go ahead and collect those two things together. That's c sub n is equal to c sub n divided by 2 plus 1. Right? Now for those in 235, what is this thing? Have you done recursion yet? Recurrence relations? No, not yet? All right. Well, this is a nonlinear recurrence relation because this is not a linear function. A linear function would be something like n minus 2 or n minus 3 or something like that, or with a coefficient out front. And you could have any number of them based, any number of previous terms in the sequence. It's non-homogeneous because it's not just dependent on the sequence, it also has this non-recursive cost over here. So this is the recursive cost, this is the non-recursive cost. I could solve this, but this isn't math, right? I don't want to solve this. Instead, I want to use another tool called the Master Theorem. All right? And for this one, I do want to make sure that I copied it correctly. I'm pretty sure, I'm 90% sure that I can do it off the top of my head, but then of course, if I do it wrong, then it's on YouTube forever, me doing it wrong. All right. So, Master Theorem. Let t sub n be a recurrence. Right? And there are a bunch of other technical stuff, like you need a base case and stuff like that. Forget about that. We're just going to apply it, right? Let t sub n be a recurrence of the form t sub n is equal to a t sub n divided by b plus f of n, where f of n is order n to the d. Right? So I've got a, b, and d here. I've got 3 different variables. Right? Then t sub n can be characterized asymptotically here, is equal to, in one of 3 cases. It's going to be order n to the d if a is strictly less than b to the d. It's going to be order n to the d, n to the d log n if a is equal to b to the d. And it's going to be order of n to the, now, okay, I'm not going to bother trying to remember, log base b of a if a is strictly greater than b to the d. Right? So in other words, you've simply got to plug and chug here. All you need to do is identify a, b, and d, and then compare a versus b to the d, and oh, it's either strictly less, or it's equal, or it's greater than. Now, if this were 235, I might even derive this and show you what it means, why it works this way. But basically, this is capturing the number of recursive calls that you make. All right? If it's 2, then you make 2 recursive calls. If it's 3, you make 3 recursive calls. This is characterizing how much you're cutting the input down each time that you make a recursive call. If you cut it down into 1/3, then b would be 3. If you're cutting it in 1/2, then b is 2. If you're cutting it up into fourths, like you only take 1/4 of the input and then you make a bunch of recursive calls, then b would be 4. right? But it has to be cut down by a certain ratio every single time. You can't just take 5 off of it. N minus 5, that would be a different recurrence relation, and the Master Theorem wouldn't apply. This is capturing the non-recursive cost. How much are you? How many resources are you expending other than just the recursion? Right? And for us, for the example that we're doing here, that's comparisons. Okay. So the idea here is that if you are doing fewer recursive calls than non-recursive work, then you can characterize your algorithm this way. If you are doing more recursive calls than non-recursive work, then you can characterize your algorithm this way. This is the intuition. But on the other hand, if you're roughly doing an equal number of recursive calls to recursive work, that ratio is kind of the same, then you can characterize it like this. Okay? So now let's go back over here. What's my A? What's my A sitting out front? How many recursive calls did I make? What's the coefficient sitting right here? 1. Right? How big or how much did I cut the input size? What's B? 2. I cut it in half. Now what's D? Characterize this function. 1 is big O of n to the d. What d would you insert there for this to be true? 0. Right? Okay. So now you need to make sure. Now you need to make the comparison: A versus B to the d. Well, A is 1, B is 2, D is 0. So would you say that this is less than, greater than, or are they equal? They're equal. Right? So by case 2 of the Master Theorem, we know that C sub n is big O of n to the d log n, but we already said d was what? 0, so what happens to it? N to the 0 is 1, so it goes away, and we get n, or just log n. Right? Nifty. Right? If you went through and actually solved it, you would get the same answer. If you went through and analyzed it directly in a non-recursive version, you would get the same answer as well. Right? Okay? If you split it up into thirds and you made one recursive call, you would end up getting log base 3 of n instead, which we've already seen is the exact same thing because all logs are the same to within a constant. Okay? All right. So hopefully you're following on YouTube because I did I'm going to skip a quick sort because I did it on YouTube instead. And so if you watch that video, I did it with the light board over here in the Henslick Hub. So if you're really interested in revisiting a quick sort and how it works, remember you choose this pivot element, you put everything greater than it on one side, everything less than it on the other side, and then you recurse on both of those. That's how quicksort works. Again, you would get. I go through the analysis a little bit. If you're really interested in how it works, watch that video or read the CS1 book. Right? What I want to show you is something new, right? Or maybe it's new. Merge sort. Right? I like it a little bit better than quicksort because it does provide a guaranteed. I don't like it any more than any sorting algorithm. Again, at the end of the day, do you implement your own sorting algorithms in practice in real life? No. What do you do? In Java, what do you do? Arrays.sort if you've got an array. If you don't have an array, if you have a list, what do you do? Collections.sort, right? Merge sort, the idea here is that, let me go ahead and think of interesting random numbers here. 5, 2, let's double it up, 8, 9, and 1. There we go. So I've got, this is my list of numbers here. All right, this is an array. The way that merge sort works is by splitting it up. It's a divide and conquer algorithm. So the first step is it divides it up into 2 lists. So it's going to divide it up into 3, 8, 9, and 1. And I'm not going to write all of the lines anymore. 3, 7, 5, and 2. Right? So it splits it up into two lists. Now we need to divide and conquer this one. So it splits it up into two lists again, 3 and 7 and 5 and 2. Right? And it's similar over here, but I'm not going to draw it all. Right? All right, we've still got two things here. What do? You split it up again into 3 and 7. Now, what can you tell me about this list right here? It's just one element, so it's sorted. Right? Likewise, this is one element, so it's sorted. So at this point, it's sorted. What I need to do now is I need to start merging these two things together. When I merge them, 3 goes first, 7 goes second. And it's only going to get interesting once I get to other things here. Right? When I merge these two, these actually get flipped, and I've got 2 and 5. ... When I actually merge these, I get 3 and 8, and I get 1 and 9. Right? So I've got this list, this list, this list, and this list. When I merge these two together, what do I get? 2, 3, 5, and 7. When I merge these two together, I get 1, 3, 8, and 9. And now at this point, now I'll go ahead and show you the detail of how this works. Because now it's actually interesting. I've got 4 things here. Right? This isn't... OK, they're not bleeding through, hopefully. That one's kind of bleeding through. That's really bad. Let me see if I've got more paper. OK, good. Now I've forgotten the numbers, dang it. Oh, there it is. All right, so I've got these two lists here, 2, 3, 5, and 7. And 1, 3, 8, and 9. OK? I need to merge these together. The way that I'm going to do this is I'm going to keep 2 index variables here, I and j. Okay? And I'm going to build a new array by merging these together. Basically, you're going to take these two things and you're going to zipper them together. You're going to merge them like this. And the way that you do that is by looking at I and j and looking at 2 and 1. Which one should go first if you're sorting this in ascending order? The 1. Right? So copy down 1 over here. Now I need to move on to the next one. Right? So j is incremented. And now I'm comparing 2 and 3. Which one of those goes next? 2. Right? And so I increment I over here. Right? Now 3 and 3. Right? Which one goes first? They're equal, so does it matter? No. It does matter when you're writing code, though. Which one should you prefer, this one or this one? I'll just go ahead and go with the left list, right? Because I like reading left to right, right? And now I'm looking at 3 and 5. Well, 3 goes next, and so I increment j. Right? And now I'm looking at 5 and 8. Which goes next? 5. And so I gets incremented. 7 and 8. 7 goes next. Right? And so I is now off the list. What happens on the next iteration? 8 versus undefined? What should I do in that case? When I've run out of things in one list or run out of things in the other list, what should I do? Just take the rest of the list and put it at the end. 8, 9, right? ... So there are a couple of phases here. First of all, there's the phase where I'm looking and comparing between the lists. At some point, one of these or the other is going to get to the end, at which point I need to stop comparing and simply just copy the rest. That could be this list or it could be this list. Right? So let's go ahead and write that merge procedure. Merge. Right? My input is going to be 2 sorted arrays, A and B, of sizes n and m, respectively. Right? And my output is going to be, and usually you want to do this inline. You don't want to create yet another array and then merge everything in that array. But for pseudocode, that's perfectly fine. Our output is going to be C, a combined array of A and B sorted. Right? I'm going to zipper them up together and produce a new array containing everything in A, everything in B, but they're all merged together so that it's still sorted. Okay? So help me out. Where did I start I? Where did I start j? Well, 1 and 1, right? So I started out at 1, j started out at 1, and I didn't show it over here, but I probably want to maintain a k. K keeps going as I copy things down. K is going to be associated with C. This is my A, and this is my B. Okay? So I, J, and K will all get initialized to 1. Right? And hopefully I'm giving myself enough room here. If not, we can just go over here. Okay? How do I do this? I need to determine which one I need to copy over, right? So let me go ahead and write an if statement here. If A sub I is less than or equal to, right? We broke ties by looking at the one on the left, B sub j, then I need to copy over A sub I. Right? So C sub k will take on the value A sub I. That's like taking this thing and copying it down here. What should I do then? What did I do with I? I incremented it. What should I do with k? I should increment it. So I plus plus and k plus plus. Right? I am leaving room here because I'm in a big loop here. Else, I need to copy over from the B array into the C array. So I'll come back up over here, and it'll be in this. Now we're in the else statement here. So it'll be C sub k. It will take on the value B sub j, and then j is going to be incremented. Oh, and then I is also incremented, right? And so there's the end of my if-else condition. Okay. Oh, sorry. J, k. Okay. That should be j. That should be k to be consistent with that. All right. Now, when did I stop? I stopped when either I fell off the end or, with a different example, it could have been j falling off the end. Right? So I continue until when? While I is still in scope and j is still in scope. While I is less than or equal to n and j is less than or equal to m. I will continue copying one or copying the other, copying one, copying the other, copying one, copying the other. At which point either I has fallen off or j has fallen off. Right? That's the end of my big while loop. Now I need to now I need to take care of the second phase, where if I has fallen off, then I need to copy everything over from j. If j has fallen off, then I need to copy everything over from I. Now you can go ahead and reason this out and do if I has fallen off, then copy over everything from j. If j has fallen off, then do this over here. It's needless when you can go ahead and roll that all into just two while loops. Right? While I is less than or equal to n, C sub k should take on A sub I plus plus, and k plus plus. And while j is less than or equal to m, C sub k will take on the value in B sub j, j plus plus, k plus plus. There. Note that these while loops are after this while loop. So I've got while loop, while loop, while loop, all in the same scope. Right? Now, why does this work? Well, if I has already fallen off the edge, it's greater than n. So this while loop will never get executed. If j has already fallen off the edge and it's greater than m, then this one will never get executed. One of these will execute at least once. I don't know which one. Who cares? Right? If you wanted to write a big if else statement and then put each one of those loops into the if else statement, that's fine. But why? It's just extraneous code. Right? Okay. With our last few minutes here, let's reason about this. Now, that's just the merge routine, subroutine. The actual merge sort would look something like this. You're given A, you're given let's see, you're given, let me come back to that. So basically you need to, the idea is that you do the splitting, the partitioning up first evenly, right? And so let me go ahead and consult this, guys. I don't want to get this wrong. And ooh, I'm almost out of batteries anyway. That's not it. Okay, there we go. All right. So we do have an if condition here. If L is less than R, right? Then we have our array is of size greater than or equal to 2. And so we do need to split it up, right? And when we split it up, we simply call, we compute the median, the middle element again going R plus L divided by 2, just taking the average. That tells me where I need to split it. I need to call merge sort on A, and then I will update L and R here, going with L up to M. Merge sort on A, and then what's the other side? If I go from L up to M, then what are the rest of them? L dot 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 M, then up to R. Where should I go? This is one partition. What's the other partition? Where should I start it? M plus 1. That's my split. So it'll be M plus 1 all the way up to R. And then I will output merge of A, or yeah, I'll go ahead and call them A and B here. Sorry, I should have been capturing those. A and B. What did I call it? Oh, that's why I called them L and R, because I've already used M. Dang it. All right, L and R, L and R. All right, my input is A here, so I don't want to confuse that with the left partition, the right partition. There we go. All right, and else output A, because it's already been merged and sorted. So here's the idea. I'm calling merge sort on the left partition, calling merge sort on the right partition, unless, how big is it? If L is greater than or equal to R, right, that means that they've either met. If they've met, then how big is the array? Of size 1. If they've crossed, how big is the array? Negatively sized, the size of 0, right? So if it's if they're not equal, in other words, I've got at least 2 elements that I still need to split up, right? Or I've got 50 elements and I need to split that up. Merge sort basically cuts it in half, putting the left partition over here to one call of merge sort, the right partition over here to the other call of merge sort, and then merge here simply takes these two things, L and R, which are already sorted, and merges them together according to this pseudocode that we just wrote over here. All right? So the idea is we make how many recursive calls? We need to set up a recurrence to look at this. C sub n will be the number of comparisons by merge sort on an array of size n. Right? Now, these are not mutually exclusive. I am making how many recursive calls here? 1, 2. So 2 recursive calls to merge sort, characterized by C sub n. How big is the array that I give the first one? If this entire thing was of size of n, then if I roughly cut it in half, then this will be n divided by 2. This one will be of size n divided by 2, roughly. You could be off by 1, 7 divided by 2, that 3.5. One of them will get 3, one of them will get 4. It doesn't matter, at least for the theoretical analysis here. Plus, now what's my non-recursive cost? This is the number of 2 recursive calls, right, on an arrays of half the size. What's my non-recursive cost here? In other words, if I look at this merge sub-procedure here, how many comparisons am I making? Let's come back over here. I made one comparison to determine that 1 should be down here. Then I moved this over. I made one comparison to see that 2 should be down here. Move this over. One comparison to move this. One comparison to move this. One comparison, and then I didn't do any comparisons after that. I just copied it all over. If they were completely interleaved, though, how many comparisons would I need to make? This is of n divided by 2. This is n divided by 2. Therefore, the combined is going to be n. About how many comparisons would I have to make? N, right? So the non-recursive cost here is n, minus 2 or minus 1, whatever you want to look at it, right? So let's pull in, and unfortunately, where is it? What happened to my Master Theorem? Oh, well. All right. You can go ahead and rewind if you're on YouTube right now. All right. So I've got something that looks like this. C sub n is equal to 2 c sub n divided by 2 plus n. What's my a? 2. Again, it's just plug and chug. What is my b? What is my d now? N is going to be order n. So what's the exponent sitting right here? 1. Right? So a versus b to the d. 2 versus 2 to the first. What case am I looking at again? This is equal. So by case 2 of the Master Theorem, I get that c sub n is order n to the d log n, right? Which is, what was my d again? 1. So unlike a binary search, it doesn't just disappear this time, but it does simplify to n log n. That's about as best as you're going to do with a comparison-based sorting algorithm. In fact, there's a theoretical lower bound for comparison-based sorting algorithms of n log n. Any sorting algorithm, this is, say, computer science 4 material, 423 if you're eventually going to take that. But you could go ahead and prove a lower bound using a bunch of tournament arguments that any comparison-based sorting algorithm will require at least n log n comparisons to sort everything. Right? It's kind of like it's like a tournament, right? If you start out with 64 teams, how many games do you need to determine a winner, right? How many games do you need to get a full ranking of everybody, right? You don't need round robin, because you can assume that if team A defeats team B and team B defeats team C, then team A would defeat team C. Now in real life you can't assume that, but this is the better team, or this is the best team. This is the second best team. This is the third best team. It provides you a ranking. If you can assume that any team that beats another team would also beat a team that they beat, then you can come up with an argument like that. Right? Now, in real life, you can't assume that, because your best player might sit on the sidelines for that. They might be injured. Right? You might not have a coach anymore, et cetera, et cetera. Right? All right. Any questions?